In this lesson, we're going to discuss corrosion from the perspective of the corrosive environments to which the materials can be exposed. It's one of the several ways that we can classify and look at corrosion, and it's useful to come at it from various perspectives, and it gives us a better overall appreciation of the subject. We could classify corrosion based on the appearance, or we can class of the damage itself, or we can base it on the corrosive environments. In another series of lessons, we'll look at corrosion from the various material classes. The goal of this lesson is to examine some of the commonly encountered environments that materials are exposed to for corrosion resistance. We will rationalize the general behavior in terms of the basic concepts that we've been introducing throughout the course. And we also want to underline and recognize some more of the natural and unnatural combinations. That is, what materials are specifically well suited for a given environment, and also which ones are particularly not well suited. Both are important to us. The examples we're going to be giving are strictly that. They are examples, and I would refer the participants in the program here to the specific literature for any given corrosion problem you want to look at. In the first slide, we can show some of the important characteristics of environments that are encountered throughout. And the important characteristics of environments are, first, the acid and alkaline nature, or the pH of the solution, is one way of measuring that. Secondly, the oxidizing or reducing environment. What is the oxidizing potential of the environment? Is it strongly oxidizing or strongly reducing? Temperature is obviously an important factor of the environment. The nature of the environment, that is it completely immersed and is a specimen wet and moist all the time, or is it alternately immersed and going through a cyclic wetting and drying, is an important characteristic. Also, there can be detrimental or beneficial species within the environment. And there are other contributions for specific environments that could include velocity or particulate or other species, application of tensile stresses, this type of thing. All of those are important characteristics of any corrosive environment that we're discussing, and what we'll do is talk about several specific environments and try to point out its own characteristics. The challenge is to match a particular material to the corrosive environment that we're desiring. And what we want to do is build in or design for sufficient corrosion resistance, but yet we don't want to overkill the situation and gold plate a lot of material. If that's the case, then we're spending more money than has to be done. So the real challenge is to match the material to the corrosive environment and have simply enough corrosion resistance for the particular service. Let's look at a couple of those characteristics in a little more detail. The next slide emphasizes the acid alkalinity of the environments, and in that we list several environments. We're plotting the solution versus the pH of the environment, and remember, the pH is a measure of the hydrogen ion concentration. The lower the pH, the lower the number, the greater the hydrogen ion, or the stronger the acidity. If you notice on that, at the high end of the scale, the hydrochloric acids and sulfuric acids at a concentration of 1 normal are extremely powerful acids. They're very strong acids having pH values of less than 1, 0.1 and 0.3 respectively. Boric acid, on the other hand, in a 10th normal solution, is a much more weak acid. It doesn't dissociate nearly as much, and we get a mildly acid, a pH 5.2 measurement. On the far extreme of that, we go to the more alkaline environments. Sodium carbonate at a 10th normal environment is 11.6, a mildly alkaline environment. Ammonium hydroxide, again, mildly alkaline, 11.6. And sodium hydroxide is a very strong hydroxide, a very strong basic solution. So in the common environments, we see that it's a nature of the environment itself to have a characteristic acidity or alkalinity, and that can vary from very high acidic values to very highly alkaline values, or it can remain neutral. Another characteristic we said is important in the environment, and that is the oxidizing potential. And the next slide shows some common environments and ranks them as to their oxidizing or reducing behavior. So on that table, we find at the top of the table the most highly oxidizing end of the scale. Concentrated nitric acid and wet chlorine gas are extremely highly oxidizing, very positive potentials for those environments. In the middle of the scale, sulfuric acid and aerated, that meaning oxygen-containing hydrochloric acid, are moderately oxidizing environments. And at the very bottom end of that scale is deaerated hydrochloric acid that contains no oxygen. So we go from very highly oxidizing to very highly reducing environments, and we have many environments in between. We can go back and recall the potential pH diagrams that we've shown in earlier cases, and on this we're plotting the electrochemical potential, the oxidizing power of the environment, as a function of pH. And we go from very acid, low pH, neutral, pH 7, highly alkaline, pH 12, versus the oxidizing power, very negative potentials representative of highly reducing, very positive of highly oxidizing. And what we can do with these boxes is look at the position, the relative position of several environments that we may encounter. If we're talking about hydrochloric acid, sulfuric acid, and nitric acid, then we have a situation where we're always talking about strong acids and we see very low pHs. Nitric acid is highly oxidizing. We'll give oxidizing powers in this range. Sulfuric acid ranges from dilute to concentrated over a range of oxidizing, and we mentioned hydrochloric is a strongly reducing acid. Boric acid is a milder acid, a weaker acid, and we see mildly acidic pHs on the order of 3 to 5 with boric acid solutions, mildly oxidizing. In corrosion in general water systems are essentially in the center of this diagram. They range from mildly reducing to mildly or highly oxidizing. And if we're talking about atmospheric corrosion, corrosion in marine environments or fresh water, we're talking about essentially neutral conditions right around pH 7 and oxidizing conditions throughout this range. Mildly alkaline environments are represented by bicarbonate and ammonium hydroxide. And in those cases, we have slightly alkaline pHs from on the order of, say, 9 up to 10 or 11 or 12. And again, mildly oxidizing depending upon the gas in contact. Sodium hydroxide is a very concentrated basic solution, a very strongly alkaline solution, and we measure very high pHs. And again, we see a range of oxidizing conditions. This is just to give us a general feel. It's useful when we're talking about the various environments to visualize the potential pH axes. And if we say, okay, we're dealing with a nitric acid solution, that focuses in on a highly acidic, highly oxidizing environment. If we're talking about a sodium hydroxide environment, we're talking about a highly alkaline environment. So it gives us a frame of reference with which we can refer to when we're discussing materials behavior in the various environments. Now, of course, the corrosion behavior is going to depend upon not only the environment characteristics, but the metal characteristics. But at this point, we're focusing on the characteristics of the metal, of the environment. Temperature is an important characteristic of the environment. In general, as the temperature increases, the corrosion rate increases. Corrosion reactions are activation-driven processes. Higher temperature provides higher activation energies, and so the rate increases. Also, the corrosion rate will increase with increasing temperature because we tend to increase the transport. Diffusion constants go up, the mobility of ions increase. This tends to increase corrosion. The contrast between a constantly wet environment, such as immersing a specimen in seawater, and a cyclic wetting and drying exposure can be an important parameter of the environment. And quite often, the wetting and drying is much more aggressive than the continual immersed conditions. The reason for that is the concentrations build up in the thin layer of electrolyte as the material dries out. Also, we form solid corrosion products, which then redissolve on occasion upon wetting. And so the alternate wetting and drying can be very important. In atmospheric corrosion, we see an interesting phenomenon. If we look at a plot of corrosion rate versus time, and we start with a dry specimen, a steel panel out on a sunny day, it's dry. If that now gets moist due to a fog or a dew, what we see is a great increase, a very high corrosion rate when there's a thin absorbed layer of moisture on the specimen. And then when it's covered with a thicker film of moisture, the corrosion rate remains at a corrosion reactions are going on, but at a much lower level. And as we now dry that out, the sun comes out again and decreases the thickness of that moisture layer again. It's the last bit of moisture, the very thin moisture film, that's the most detrimental. The corrosion rates are very high again, and then of course when it gets dry completely, the corrosion rate stops altogether. So this alternate wetting and drying is a very important characteristic of the environment. Yet another basic characteristic are the chemical species in the environment itself. And we can have both detrimental species and beneficial species. Examples of detrimental species, if we're talking about passive materials, are environments that contain chloride ion. The chloride ion can destroy the passivity, be very damaging. Also, elements in the environment that complex metal ions can greatly increase the corrosion rate. These would be detrimental examples. Beneficial materials would be things that act as corrosion inhibitors, chromates, silicates, other constituents of the environment that can be beneficial by slowing the rate, and also elements that will increase the passivity or be passivating elements.
Several examples showed how pH, acidity or alkalinity, affects corrosion rate. Examples were also studied showing oxiding environments, as was the relationship between oxidation reduction and pH. As temperature of the environment increases, corrosion rate increases. Samples that undergo cyclic exposure to a corrosive environment, wetting, drying, re-wetting, generally corrode more than samples continuously immersed in the same corrosive solution. Detrimental chemical species often found in corrosive solutions include chloride complex, which destroys passivity. Beneficial species include chromates and silicates, which reduce corrosion rates.
Now let's look at some specifics of those overall characteristics in given environments. And we're going to go through here very rapidly, but it's more important here that I'm trying to give you an overview of these important characteristics than the technology of the particular corrosive environments themselves. You can refer to general texts and find that. We're going to talk briefly about atmospheric corrosion, underground corrosion in soils, corrosion in waters, acids, and alkalis. You'll encounter many others in service, and what I would do would be refer you to the literature, and what I've done is I've brought a series of books here that just are examples again of the wealth of information that's available. You can find entire books on the corrosion in the pulp and paper industry. You can find entire books written on the process industry corrosion and the chemical process industry. Those are two examples of NACE publications. You can find monographs and compilations of data on corrosion of metals in atmospheres, atmospheric corrosion. That's an MCIC, a Metals and Ceramics Information Report. You can find an entire volume written on the corrosion of metals in marine environments, again, where the data has been summarized and brought together in those particular environments. So what you can find is a whole series or a wealth of information in a particular environment. And those are fairly easy to track down in the literature. What we'd like to do is go through some examples here where we're going to talk about corrosion in some important specific environments and leave it to you to follow up in the environments that are most important in your particular instance. First, we'll talk about the classification of atmospheric corrosion. We can break the entire field of atmospheric corrosion down into several based on the type of atmosphere that we're exposing the environment to. And we can break that down into industrial, marine, and rural. An industrial environment is that typified by the environment we would find around this chemical process plant or a steel plant. It can vary from a mild industrial environment to what we would refer to as an extremely aggressive. The metals that are exposed around the top of a coke oven in a steel plant, where we have effluent of vapors containing corrosive gases from time to time, can be an extremely aggressive industrial environment. Contrast that to what we would find in a marine environment. And again, this is an example of an offshore platform where we have in this case, metals and components exposed to the atmospheric corrosive vapors, sea mist. We have tidal wetting and drying action in this particular area. And we can contrast that to the atmospheric corrosion conditions that we would find under rural conditions. And this is just a nice photograph of a country lane. Now, obviously, the corrosion behavior of metals, the rates at which they'll corrode and how these metals will be maintained is going to vary upon the aggressiveness of the environment. A very harsh industrial environment will corrode metals much more rapidly and a wider number of metals than we would corrode out in a more benign rural environment. So one of the things we want to know in atmospheric corrosion is what's the characteristics of the environment itself. Also, an area that's becoming more and more important is corrosion indoors, in indoor applications. And there again, we can break that set of environments into a smaller set. We can talk about industrial indoor atmospheres, such as you would find inside manufacturing and chemical plants. Commercial, such as dry cleaning establishments and retail establishments, and then our own household. Within your own household, it matters if you're talking about corrosion in the family room or if you're talking about corrosion in the laundry room. In the laundry room, obviously, the humidity's higher, the types of chemicals that might be in the vapor are higher, this type of thing. So indoor atmospheric corrosion becomes more and more important. The drive toward using more and more microelectronic parts, personal computers, process-controlled, microprocess-controlled equipment that's running our TV sets, that's turning on and off electrical devices around the house or in plants. These devices continually are made out of smaller and smaller cross-sections, and they become less and less tolerant to corrosion. The whole corrosion in electronics area is a very extreme portion of corrosion science and technology. What are some of the factors that affect atmospheric corrosion? Well, one of those is the moisture. What's the moisture level in the environment? And one of the things we find that's most critical in determining atmospheric corrosion rate is simply the time of wetness. If we expose panels outdoors around various sites in the country, one of the greatest correlations to corrosion rate is how long were the specimens wet. If you put them out in Arizona where it's dry and low humidity most of the time, the corrosion rate is very low. If you put them on a seaside environment where it's moist all the time and humid, the corrosion rate would be much higher. There's a concept called critical relative humidity that's shown in the next slide. And this slide shows the data is taken from Vernon's results back in the late 1920s, early 1930s, as presented in Uhlig's book on corrosion control. And what we find here is we're plotting the corrosion rate, measured as weight gain, as a function of relative humidity. And these are for steel specimens exposed to a moist environment containing a small amount of SO2, acid gas. And what we find is the corrosion rate is very low until we reach what's referred to as a critical relative humidity. That's the point at which moisture begins to penetrate or to form and absorb a liquid layer on the specimen. And when that happens, when we get condensation, the corrosion rate increases at that critical value and higher relative humidities. Unfortunately, the critical relative humidity is a function of the environment. It's a function of the metal surface, how well it's cleaned, what other environments might be on it. So it's not a design parameter we can use, but the concept is very real. And one of the ways we can control atmospheric corrosion is to maintain humidities at very low values. The temperature is an important criteria in atmospheric corrosion. Again, as temperature increases, typically the corrosion rate increases. The types of contaminants that might form on the surface. And these are, you could imagine if we have a dust which when it gets wet gives off acids, becomes acidic, that could be a very corrosive environment for us. Even if the dust and particulates that form on the surface are innocuous and don't really dissolve, giving us alkaline or acidic conditions, they still promote condensation more quickly than we would have on a smooth, clean surface. So we can either have active or inert particles, which will both contribute to the corrosion. The particles themselves can give off acidic or alkaline components. So the types of debris that form on the surface are extremely important to us. Let's look at the corrosion behavior of some steel specimens in atmospheric corrosion. And what we're looking at here is the corrosion rate increasing on this scale as a function of time in years. So we're going from 1 year out to 8 years exposure. And if we plotted we don't have it on this scale, but if we had just a mild steel specimen, its corrosion rate would increase and would essentially continue to increase at a reasonably constant rate. What we find is if we put a small amount of copper, 0.2 copper in the material, the corrosion rate starts off fairly rapid, but then goes to a much lower rate. Copper and phosphorus are even more beneficial. Small amount of nickel is very beneficial. And if we look at the class of materials that we refer to as the high-strength, low-alloy steels, these are steels that contain some phosphorus, some copper, chromium, and nickel, all beneficial from the corrosion standpoint. We find the corrosion rate starts off fairly high, but then levels out over a long period of time. This is some of the data taken from Larrabee's work and again reported by Uhlig in his corrosion handbook. This is put to practical use by designing structural parts out of these weathering, or also referred to high-strength, low-alloy steels. And here you see several shapes that are available, I-beams, squares, rounds, so forth, that we can make materials out of. One of the distinctions of these over the characteristics of mild steel is that the appearance of the corrosion products, we still have a considerable amount of corrosion going on here, but the types of corrosion products are more dense, they're more adherent, and they stop the corrosion rate more effectively. There's a great wealth of data on corrosion rates of steels over various parts of the United States. And there are test sites that have been set up and maintained by ASTM, and experiments where tests have been run on standard materials, steels and copper and zinc and other coated materials, over many, many years. And through the corrosion data program of NACE and the National Bureau of Standards, some of this data is available in computerized form. And we show that here in bar graphs. The point here for this is for galvanized steel, zinc-coated steel, after 20 years exposure, and the height of the bar represents the corrosion rate of identical materials in various places. And what we find here are the bars are much greater up in this part of the world, where in the Northeast, where the corrosion, the time of wetness is greater, and also the possibility of having industrial atmospheres is greater than out in some of the plain states. And so we can see the corrosion behavior of galvanized steel as a function of those environments. The ways that we control atmospheric corrosion are typically by using coatings on steel, and we can either use organic coatings, paint films, or we can use metallic coatings such as zinc and aluminum, sacrificial coatings, or noble coatings where we put a noble metal on the material. We move to corrosion-resistant alloys. We use copper alloys. Aluminum alloys are good under most atmospheric conditions because the conditions are fairly neutral. And one of the other schemes is to control atmospheric corrosion by removing the relative humidity completely. And so we go in and we air condition the control rooms where we have sophisticated electronic equipment that we want to maintain from corrosion. We keep the humidity down below that critical value for relative humidity, and we stop the corrosion.
Classes of atmospheric corrosive environments include industrial, marine, rural, and indoors, industrial, commercial, and residential. Amount of moisture or relative humidity often has a tremendous bearing on corrosion rate. Higher atmospheric temperatures often increase corrosion rate. Contaminants in the atmosphere can promote corrosion themselves or indirectly increase corrosion rate by causing moisture to adhere to the sample.
Okay, let's shift gears a little bit and talk about the important characteristics of corrosion in soils. Again, a very important aspect when we talk about corrosion of pipelines and steel tanks, that type of thing. We have many engineering structures that are buried in the soil. This is an example of some test evaluations that are going on for a buried gas transmission pipeline. Natural gas is transported through that pipeline at high pressures, and obviously it's important to maintain the integrity of the pipeline. What are the characteristics of corrosion reactions that can occur in the soil along that pipeline? Here again, we've exposed this pipe by digging out what we refer to as a bell hole so that we can get at and examine the pipe. The corrosion reaction and the corrosion process is the same in any environment. In order for that corrosion to occur, we need an anode, a cathode, we need an electronic path, and we need an ionic path for the solution. In this case, the ionic current is transported through the soil from the anodic sites to the cathodic sites. If this was a pipeline, the anodes and cathodes would be separated, the electronic current flowing between. On a pipeline in a given soil, we can see concentration cells set up. This is a diagram of a cross-section through a buried pipeline, the soil level. And at the top of the pipe, it's typical to have a higher oxygen concentration than we have at the bottom of the pipeline. That will set up what we refer to as an oxygen concentration cell. The area of high oxygen concentration will become the cathode, top of the pipe, and drive a corrosion reaction to the anodic side of the pipe. And this shaded area here shows the area in which the weight loss corrosion would occur. So one of the things that we look for on pipelines or buried steel tanks is if we have exposed steel at top and bottom, we find the possibility to set up a corrosion reaction driven by the potential difference between the high oxygen and low oxygen area. Some of the characteristics that are important in soil corrosion are listed in the next slide. And what we call out here as being important are the electrical resistivity of the environment itself, and we can measure that with resistivity or conductivity measurements, the amount of aeration and or permeability in the environment. Again, the higher the aeration, the higher the oxygen concentration, the more permeable, the more moisture can move through the environment, the more likely corrosion is to occur. The acidity or alkalinity of the environment, the pH, is an important contribution. And the final one we'll discuss is the presence of bacteria. We find that some bacteria can, in fact, greatly enhance the corrosion of metals buried in soils. Let's look at some of those characteristics in a little bit more detail. And the next slide shows some typical values or a range of values that we can see for the resistivity of various soils to corrosion, or excuse me, the resistivity measurements. And what we're showing in this slide is a column of resistivity measured in ohm centimeters, and the higher that value is, the more resistance there is to current flow through the system, as a function of the percentage of a pipeline that required repairs. The higher the percentage requiring repairs, the greater the corrosion rate. So what we find is that when the corrosion resistivity is high, when the resistance to current flow is high, the top couple columns on the scale, if it's 8,000 ohm centimeter or 11,450 ohm centimeters, the degree of corrosion, the percentage of pipeline requiring repairs, is very small, 3 to 6%. On the other end of the scale, if the resistivity is low, if electrical current can be passed very readily through the soil, represented by the 4,000 ohm centimeter and the 1,000 ohm centimeters, then we can see rapid corrosion. This data is taken from underground corrosion, NBS Circular 579 by Romanoff's work. And essentially, we can classify corrosivity of soils due to the resistivity. If the resistivity is from 0 to 2,000 ohm centimeters, we generally refer to that as a corrosive soil. If it's between, on the order of 2,000 to 5,000, it's mildly corrosive. If it's greater than 10,000 ohm centimeters, we refer to that as being a non-corrosive soil. Those are relative values, but essentially they're fairly well accepted. Another characteristic of the soil is this aeration or permeability. And that affects not only the oxygen concentration, but the ability of moisture to penetrate to the metallic structure and also to be removed and move away from the structure. That's controlled by soil characteristics such as particle size, clay soils versus sandy soils, and so on and so forth. The soil acidity we mentioned as being an important parameter for soil corrosion, and some of the typical data for soils is shown in the next slide on that. In this slide, we're showing the total acidity measured in milligrams per